I'm the captain of Formula UBC for this season. Tonight we're just going to go over a brief presentation. We'll talk about a little bit about what the team is and what the competition is, for those of you that don't know. Then we'll have each of our technical leads go over their projects for the year, kind of what they're responsible for, and some of the notable features on the vehicle this year. Hopefully we'll keep that relatively quick, and then we'll get to the main event, and we'll pull the veil off the car and have some time for everyone to take a look and ask questions and meet the people on the team as well. So we'll get started here. Our team has about 50 people, and it's been around since 1991, so we're one of the older engineering design teams in UBC. We're broken into 10 sub-teams, which I'm not going to read them all for you, but you'll see most of the technical ones today. And then we also have a business team to do a business presentation, which is one of the events in competition, and a software team started up this year to work with some of our data processing and that side of the analysis. So the competition itself is called Formula SAE, which is an engineering design series that is put on by the Society of Automotive Engineers. It's been around, I believe, since the 80s, so it's pretty well established. And the purpose of the competition was to give engineering students hands-on activity that was relevant to industry before they had to go find a job. So it's focused on that from the beginning and has grown from a competition in the States to be a really international and worldwide competition. There's over 500 teams worldwide, and they add new competitions every year, so it's up over 12 competitions worldwide. We go to Formula SAE in Michigan, which is the most competitive competition in North America. There's 120 teams at that competition, and we'll be heading there. We'll be leaving next Friday for the competition May 8th to 11th this year. At competition, there's a variety of static and dynamic events. The static events are the business presentation, where you're pitching the team as a company for a business case that they give you ahead of time. You do a cost event, where they give you standardized tables where you have to cost out each part on the car, and it's to evaluate the trade-off between the price of the vehicle and the performance of the vehicle. Then you do a design review, where they have a bunch of industry engineers that have at least 5 years of experience in the field, automotive engineering, and they'll ask you why you built everything on the car the way you did, and you'll have to justify it in front of them. Once you get through that, you get to the actual driving portion of the competition, the dynamic portion, where they do an acceleration sprint, which is 75 meters in a straight line, and the fastest time gets the most points. They do a figure-8 skid pad test, which evaluates the vehicle's cornering capabilities. They do an autocross event, which is a really tight course with cones, and you get 2 drivers, 2 laps each, and the best lap time counts. The results from the autocross event determine what time of the day you run for endurance, which is the last and most important event. It's worth 30% of the points of competition. And that event is 22 kilometers around an autocross style course, split between 2 drivers. And then at the end of the event, you get points based on your overall time as well as your fuel economy for the event. So throughout the week, they really evaluate every part of the vehicle, from why you built it the way you did and what you considered, to how it performs on the track and how economical it is. So our goals for this year were mostly to better understand the vehicle. We didn't do a super huge design iteration. There's smaller incremental changes. Last year we had a relatively successful year. We ended up placing 38 out of 120 teams. But with that placing, we had a lot higher potential, because in the endurance event, which I mentioned is worth 30% of the points, we had a minor electrical failure that led us to get 1 point out of a possible 300. So it ended up hurting us quite a bit, but before that, we're on track for probably a top 20 or 15 finish. So we're happy with how the car performed, other than a few minor issues. So we're aiming to better understand the vehicle, try and improve the reliability of the vehicle while maintaining the weight and performance that we had last year. And to progress in the design portion, we want to do physical testing to validate all of our simulations. Simple stuff from putting stuff on a bench, making sure it behaves the way we want, to more complicated full vehicle level testing and using the data acquisition system on the car to see how the car is behaving on the track and correlate that to what we'd expect. And then beyond all that, we work with a whole bunch of really talented sponsors and machinists in UBC and Lower Mainland in general to help build the car that we have today. So that's kind of the process of this year. And I'll pass on to Jeff now to talk about the aerodynamics portion of the car.
Hi everyone, my name is Jeffrey Jadlowski and I'm the aerodynamics lead this year. Thank you for everyone coming out. Some of the projects that Aerodynamics worked on this year were to better understand the aerodynamic balance of our vehicle. Our vehicle runs a multi-element front wing and a multi-element rear wing. This year we added 2 side pods. The side pods are effectively used to create cooling ducting for the radiator. We've had significant issues with heat rejection for our engine in the past, and so this was a big project for the aerodynamics team to try and meet some of the necessary performance metrics for the side pods to make sure that the radiator is actually getting enough air. So that was a big project that we put a lot of time and effort into. The next one is continuing our computational fluid dynamic validation. So on the aerodynamics team, we use a lot of complicated software to try and figure out what the air is doing around our car. This software is used in industry, and it's standard kind of across the automotive and aerospace sectors. So first we start with a 2-dimensional sweep, evaluating simple geometry. Then we introduce real life variables such as like a ground or turning effects. This year we focused from the ground up and worked on what's known as the ground effect. So that's effectively when the wing changes the height relative to the ground in the front. It actually causes a venturi effect and can create more downforce, which is something that we evaluated closely from our previous year's wing. Next, I'll pass it over to Scott again, who will talk about the chassis.
So as I mentioned before, the chassis didn't change that much because we had a relatively minor design cycle. The chassis team is responsible for the main frame of the car as well as the impact attenuator and crash structure. So we made a space frame chromoly steel chassis and kind of stayed similar to our design last year. The main notable change this year was adding a structural composite panel under the driver. The reason for that was to allow a little bit more flexibility with the suspension design, which we'll talk about a little bit later, as well as the driver seating position, and as well as to try and build up a little bit more team knowledge on the structural composite side and try and understand how to model and simulate and predict how that'll behave when it's a more complicated material than steel in the vehicle, which Fred will talk about a little bit later as well. So that was the main project this year, and I'll pass it on to Colin to talk about the controls subsystem.
Sure. So the controls is sort of short form for driver controls and ergonomics. So really this sub-team is generally in charge of everything that the driver is in contact with, anything that is going to take your driver's intentions and get them into the vehicle. That's what the controls team is in charge of. So you need to make sure that it's as comfortable, responsive, and you have to have some level of safety as well as comfort, and all that kind of stuff is kind of combined together into what makes the control system. So you can see sort of an overall render of what mostly constitutes the system that we have. So this year there's again cool better lighting. Again, not huge changes. A lot of it is sort of iterative and moving forward on stuff that we've worked on in the past. So improving adjustability, the main thing there, we redesigned a completely new design of the pedal box assembly, which you can see here. It's now adjustable purely without tools, which is a really cool thing. Also a little bit lighter, and everything's just a little bit nicer packaging. So new pedals is a part of this year's biggest projects. We did change a lot of stuff with the actual driver compartment cockpit area. As Scott mentioned, with the panel on the floor, it actually opened up a lot of our sort of freedom with what we could do with the seat. So the seat back and bottom are sort of integrated into the car a little bit more, and it's all sort of one piece, and it's a bucket that we essentially use to make a little insert that fits inside of it for the driver, and it's a custom fit insert specific for the driver it's going to be driving at the time. Additionally, we had small changes with the steering wheel. Probably the most notable thing is we made some new grips that are made from moldable plastic that we could then 3D scan and print molded hand-formed grips out of. So they're actually like custom fit for our drivers as well. So that's pretty much covers everything for controls, I think, and I'll pass it over to Carlos with the electrical system.
Hey guys, my name is Carlos. I'm one of the co-leads for the electrical sub-team. So as Scott mentioned, last year we had an electrical failure during our last race, which was the endurance, which was worth a lot of points. So this year we made it kind of the priority to make sure that the electrical system is as reliable and as robust as can be. We had the pleasure of recruiting really talented new members to the team, and we were able to accomplish a lot of tasks. So as I mentioned, our design goals were increasing the modularity of our system, improving the reliability so we make sure that no mistakes happen at competition, as well as just making sure that we document every process and everything that we design. The system that we were working with in the last year was a system that not a lot of us were familiar with since we came into the team after the design was made. So it was hard to troubleshoot, and it was hard to just implement new things onto a system that we didn't know too much about. So as you can see, it's hard to see on the bottom left image, that was our previous system. It was just a nest of wires going everywhere. It was hard for the engine team to access parts. It was just kind of complicated overall, especially on the troubleshooting side of things. So this year what we did was move from a relay board to one that was controlled by power MOSFETs, and the way that works is just controlled through a microcontroller, and we're able to just distribute power more efficiently throughout the car. We also work to implement a body control module, which is responsible for the shifting and the DRS actuation of the car, which you can see on the top image. And the overall system that we have now in the car was able to be reduced to this. So you can see the modularity, how we have the engine harness, we have the main trunk out here, and then we have all the sensor harness. So it's a lot better for troubleshooting and just implementing what we want to implement and going forward. Here we have one of our members design the dash bulkhead, which is where we can put all the sensors organized in a way that we're able to see what channel goes to what pin on the dash, and we can record data more efficiently. Also, we use methods such as concentric twisting so that our harnesses are more reliable and have more strain relief. That was also implemented through service loops. That way, if you tug on a wire, it's less likely to be affected by all the friction and all the vibration that a car has. And that's pretty much the gist of it. I'm going to pass it over to Jerry to go. Oh, sorry, Freya to talk about materials. Thank you.
Hi, I'm Freya. I'm part of the materials team. So the materials team does a lot of testing for the other sub-teams, because that takes, allows them to focus more on design, and we can come up with more composites and things, as that's a newer field of research. So the first thing that Scott had mentioned was the floor closeout. So it had removed some of the chassis tubing in between the floor, and it was replaced by a sandwich panel, which consisted of carbon fiber on the outsides and foam in the middle. So on the left, you can see us we made 12 little samples following a standard, and then we put it into a 3-point bend test, and this allowed us to see where it would fail in shear, which is the most common way it would be in the situation of loading. So in order to connect the seat and all of the other controls that need to be connected to the sandwich panel, we have to do some insert testing. So we made a jig to be put into the tensile tester, and as you can see on the right, there shows the values of them. So then we were able to see if the inserts would hold up under our loading conditions. Our second project that we worked on was changing the rear axles that are currently sealed to be carbon fiber. So this would allow us to save weight, which is a big thing for our car. And by doing this, we created a jig, and then we were also able to put this into a tensile tester to see where it would fail. So based on our dimensions, it failed at approximately 700 Newton meters, which is not enough for our current loading situation. So we're going to have to work more on that, potentially redesigning some of the drivetrain if this is to be implemented next year. The third project, we worked alongside suspension. So for the suspension pull rods, we tested them to about 4 kilonewtons to see if they would withstand the loading conditions as well. And we did some fatigue testing for the A-arms, so some cyclic loading to about 10,000 cycles. So, and then I'll pass it off to Jerry, who's engine lead.
Hey, I'm Jerry, this year's engine lead, and engine team is responsible, obviously, making engine and making sure the car runs and performs as what the driver and what the competition determines to be the best. And we do so by running a Honda CBR 600RR race bike engine. And we've used this engine over the past couple of years. It's proven to be fairly reliable, so we're sticking with that. For this year, a couple goals for our team was, first of all, to better utilize a engine simulation software. And by using the software, it essentially allows the team to validate new designs before actually manufacturing it. Because otherwise, if you make something and it doesn't work, it's a waste of material and manpower. And we relied heavily on the engine simulation software to design our new intake manifold and our exhaust manifold. And we designed these new parts because our cars spent a lot of time operating between 7,000 and 11,000 RPM. And to be able to perform better in, let's say, acceleration, or more importantly, in endurance, where there's a lot of corners, we wanted to improve the power in that range. And on top of making new mechanical components, we had to refine our engine calibration, and that's done through a Howtech ECU, which controls all the engine electrics. And we spent a lot of time on a chassis dyno, where we would make power poles with the car and analyze the data afterwards to improve throttle response and allow the engine to basically run more accurately according to what we actually wanted to run. And on top of that, we achieved better drivability and response. And but these components obviously look quite complicated. So if we weren't able to make them as how we designed, it wouldn't be good. So we spent a lot of time in design phase of this year to identify the material and the manufacturing processes we can utilize this year. And we basically worked around that to create a design that we know we can manufacture properly and achieve the performance we wanted. And as with usual, we want the engine to run reliable and trouble-free. So this figure represents the power and torque output of this and last year's car. The solid lines you see are this year's car. The dotted line are last year's. Blue line is the power curve. The orange line is the torque curve. So as you can see, our power curve basically begins almost 1,000 RPM earlier than before, and we can achieve the same power and torque earlier than last year. At the same time, we were able to sustain the overall power for longer throughout the RPM range. And that's basically it for engine. And on top of the intake and exhaust projects, there were a lot of other projects, such as a brand new fuel tank. We worked with Aero for the cooling system, and we removed a oil cooler for saving weight. And we're also working on developing a new muffler based on the frequency that the engine ran the loudest. But that didn't really work out this year because the muffler itself blew up. Yeah. Anyways, I'm going to pass on to Connor, who's the drivetrain lead.
Hey guys, my name's Connor. I'm the drivetrain lead for this year. The primary goal for the drivetrain subsystem was to create a system that was lightweight and efficient while maximizing power transfer from the engine to the rear wheels of the car. We used topology optimization software extensively during our design process to create lightweight structural components, which we manufactured from high-strength aircraft-grade aluminum. One of the major features of the drivetrain assembly this year is a fully removable rear axle, which we can remove without having to adjust any of the suspension or engine assemblies. And so that means when we're out on the track, we can tune parameters in the differential or perform maintenance without having to influence any other sub-team's work. We also spent some time optimizing the final drive ratio to try and eliminate the need for driving in first gear, which makes the car easier to drive and requires less shifts for the driver. I'll now pass it on to Graham, who's the suspension lead.
So I'm Graham, I'm the suspension lead for this year. A lot of the design work that we did on suspension this year was based on testing that we actually did last year during the summer. So we did extensive testing on ride rates and roll rates, which helped us to, we changed our spring rates and roll rates. A lot of what we do in suspension is kinematic modeling and tire modeling, so we work on everything that connects the tires to the chassis. because the tire is the only thing that's in contact with the road. It's really important to maintain that contact patch. Scott mentioned, and actually Freya mentioned, our new front roll bar. You can't really see it in this rendering, but you can see it on the car when we unveil it. But that actually connects to the sandwich panel. So that was a main benefit of having a sandwich panel this year, was to connect that without having to add tubes into the chassis. We also did a fair amount of bench testing. So this is just an example of damper dyno testing, but we also tested our roll bars, as well as evaluating the actual suspension geometry. So we tested our motion ratios and our bump steer and other things as well. I think Scott's got closing remarks.
Yeah, so let's wrap up here real quick. I'd like to finish off by saying thank you to all of our sponsors. We wouldn't be able to do anything that we do without having the support that we do from a whole bunch of sponsors, that some of which are here tonight. And all of them are on our banner, which is kind of the back there, so take a look at them. We really couldn't do anything without it, so I'd like to give them a round of applause. Thank everyone for And now that you know a little bit about what's on the car and some of the notable features, we'll pull the veil off and give you a chance to take a look for yourself and take a closer look at some of those parts we mentioned. So I'm not sure what the best spot's going to be to stand here. Maybe to slide around to this side so you can see as we pull it off. And then,
Yeah, you want to be in the front, probably.
Yeah, I think we should have those.
We can't touch it.